Today we're going to live code the expanding universe, which is actually fun and easy, and we'll learn a lot. We'll start with this blank graph. First thing we'll do is add galaxies to our model. So we'll start with a blank array, and then for every 100 million light years up until about 50 billion light years, we're going to add a galaxy. So say galaxies.push, and then we'll give it its x, and that's the distance to the galaxy, and then x0, which is our initial distance to the galaxy, so we can refer to that later. The next thing we want to do is draw that. So ctx, we're going to just get the graph like that. That's its ID. It's already available to us. And then we'll say draw, and we'll make a draw function. And the first thing we'll do is just refresh the graph. So setting its width to its width will do that. Now we want to draw these rectangles, these galaxies. So fill style white, and then galaxies dot for each. So ctx dot fill rect, and we'll go g dot x. And then we'll put that down here, and we'll make it look like that, and we'll see what that does. Ta-da, there's our galaxies. So in an expanding universe, they should be moving away from each other, right? We will animate this so we can set an interval. And then what we'll do is say all the galaxies should be moving away. So we will set their distance to another distance, something farther, gx plus, and we'll use h, that's Hubble's constant, times its distance. So g dot x. And we simplify this right here. We can just say plus equals. There we go. And then they should technically be moving away. So let's just draw that again to update our view and see what happens. Oh, h is not defined, of course, so we'll set our h equal to that. All right, now the galaxies are moving away. But we actually don't want the galaxies to move away. Since we're modeling the expanding universe, but we're looking back into the past, the universe will be contracting. It'll be expanding in reverse. So to make that happen, all we need to do is set this equal to minus, and now all the galaxies are moving in. The next thing we want to do is define a photon. We'll just call that x, and that'll be its position, and it'll move around the same way. So we'll say x, its new position will be, it'll move by the speed of light, c, plus h times x. Since we're doing it in reverse, this will be a minus sign. And then we need to define c, that's 1 million light years per million light years. And let's draw that as a yellow box. ctx.fill style equals yellow, and then ctx.fill rect, and we'll say x. Put that down there. All right, let's run that, see what happens. All right, we have the photon meeting the galaxies. Since it's happening in reverse, that's actually when it's leaving the galaxy and headed towards us. And we want to record when that gets hit. So we'll say if we don't have a time, then we'll move the galaxy along. And then we'll test to see if its position is less than or equal to the photon. If it is, we'll say g.t equals t. And one thing we need to do is create our time variable and then advance that along too. So if we run this, it should all look the same, but now we should see they stop moving. We can also color code it. So hit galaxies are going to be shown in red, otherwise white. So if we run that, okay, now they're being turned into red. So that means they've been hit. The last bit of data we need is the redshift, and we're going to use the velocity to determine its redshift. We're going to say its original velocity is c and its new velocity is this. We can relate that to a change in wavelength. So we'll say z equals c divided by this. Okay, and since we would normally say 1 plus z equals that, we'll put this minus 1 here, and then g dot z equals z. So it should still look the same, but now our data should have a redshift. Oh, galaxies. Okay, we have a z, we have our initial distance, we have the recorded distance, and then we have the time it happened at. So let's now graph that. We're going to change this galaxies variable to data, because that's going to be our data. And we're going to move all of this into its own function. Function run. Okay, and now we don't actually need this interval. We'll just do while z is less than 6. That should be good enough. So that'll set up that. We have our data. So let's draw that. CTX dot begin path, and then CTX dot move to. I want that to be the origin, so we're going to need to translate the graph down. So X stays the same, but the vertical will be down at the bottom. Okay, move to, all we need to do is ctx.line to, and we'll put in our g as .z, so we're going to give this a zoom, and then we'll put g.x, and that needs to be negative because our graph is upside down like that. All right, and ctx.stroke. We can get rid of our photon here. We should also give it a color. ctx.stroke style equals white. And might as well give it a line width equals 2. So now, hopefully, we should be able to run this. We got to call the run function. And then we should be able to draw the data we have. Let's see how that works. There's no zoom z. We got to define that. Okay, we have a line. Let's put some labels on here. So fill style equals white. And then for var I equals 0, this will be our redshift labels. To I is less than 6. We'll just put that there. Fill text I. Let me do I times zoom z. We go -2. That should be good. So we should be able to. Okay, we got our labels here. Let's zoom this down a little bit. And so right here, our X, we'll put in dot zoom. Okay. Now I know what Hubble's constant will be to get us some decent data. So I'll just set that right now. Give us an idea of what we're looking at. Whoa. It's way up there. So let's keep zooming it down. All right, that looks good. So this is graphing the distance with the redshift. And that's the distance that the galaxy gets contracted to. That's its original distance when it emitted the light. So we're going to do something similar for the initial distance and also the time. This will be basically what happens when you multiply the speed of light by the amount of time it took to get from one galaxy to the observer. So there's GT. We'll distinguish these and put some set line dash equal to 10, 10, and maybe on this one up here, set it to 40, 40, and we'll draw that. All right. So this is the distance that it started at. That's called the co-moving distance. This is the distance that it ended up at. That's the angular diameter distance. And this is the light travel time distance. That's the time it took to get there times the speed of light. So those are the three distances we get from our model right here. Now this, as we talked about in the last episode, is a exponentially expanding model. It has a static expansion rate. So h gets set and it never changes. And that is not actually how things work. So what we're going to do is set this to 0, h0, that's our initial, and then we're going to have an h. So we're going to need to update that h. We can do that right here at the bottom of our loop. We say h equals, and from that last video we know the formula for this. It's actually the square root here of what we're going to take is the matter density, which is 0.3 in our universe, times 1 plus z to the third power. And then we're going to also add the dark matter energy, or dark energy density. That's 0.7. So that right there should give us an evolving expansion rate. So let's run that. Now we see we get something way different. That's because this isn't the right way to measure redshift when Hubble's parameter is changing. This only works for a static Hubble's expansion rate. So we can get around this by adding a second photon. We want to find out how the expansion of the universe actually changes over time, and we use a second photon to do that. So let's say x2 equals 0, and we're going to say x equals 0.1. We're going to give it a little head start. So now instead of updating one photon, we're going to update 2 photons. And now we're going to take basically the distance between them, x minus x2 divided by the original distance between them. So that's the 0.1 I put up there. And then we have our z, which is our minus 1, to get that right. So let's try that. And there it is. This is our universe. This is the angular diameter distance turnaround. You see it gets lower here. And here we go. That's the expanding universe. This is going to be, this will predict it. And it's really just this little bit of code right here. So what can we actually do with this? Well, we talked about in a previous video, let's see, Pantheon plus shoes data release. Here we go. This is our supernova data, and we can actually download this and use it right in our graph. So here's the data. We have we want the raw data, so we can just grab this URL. Okay. What we're going to do is fetch this URL. So there we go, data, fetch URL. Okay. When we get a response, we're just going to want the text of that. So once we get the text, we can start processing it. Now the first line is just headers here. So we're going to ignore that line. We're going to say lines equals text dot split, and just based on a new line. Okay, so for var I equals 1, since we're going to skip the first line, and we also want to skip the last line because that's blank in this file. Lines.length minus 1. Okay, go through those lines. Now what we're going to do is fill up a supernova data object. So we get a blank array here. We can say sn data dot push. What we're going to do is do its z value is this third column here. So line element 2. So we'll say lines. Oh, we got to split this line up first. So var line equals lines dot split on empty space. Okay, so now we say line 2, and we want that to be a number. Okay, from this file we also want mu, that's our distance modulus. So that 2, and then we're going to say that's in the 11th column there. And then we have an error too. We can grab that. Line 11. Okay, so now we have this data. We actually want to take a look at it first. So we got to do some conversions. What we're going to do is actually set the z value right here. And the mu value, we need that too. Now, we're going to take the mu and we're going to convert that to a luminosity distance. So it's dl, and that is equal to the power 10 to the mu divided by 5 minus 5 power. Okay, now that will give us something in megaparsecs. So we're going to cheat. We're just going to grab this line of code here. That'll convert our parsecs to light years. So times parsec to light years. And we give it a co-moving distance by dividing the luminosity distance by 1 plus z. So now we can store that right here in our data. DC. Yeah, I think that should be good enough. And now let's go ahead and draw that data. So this is what we had before. We're going to go through each supernova, right? And we have a co-moving distance, so we're going to do CTX fill rect. We're going to set that at sn.z times our zoom and sn.dc, and that's got to be times the zoom. And we'll just make that, and we'll make those red. CTX.fill style equals red. Now we should get some dots. Oh, res is not found. Got to do a little arrow here. Ta-da! Lines dot split is spelt wrong, so we'll find that. There we go. Split. And I don't see our data. Where did it go? We got to do the minus here. I think we got to do minus here. And I'm still not seeing So let's see. Oh, we probably got to draw it again after we've done all this. So, draw. And ta-da! There's the data. So, it should be matching this line. Looks like we're a little high here, so we can say, what if our constant is this, 0.8? See, that'll move a little bit. That's a little more close. What we can actually do is figure out programmatically what value of h is the best fits here. So let's say h0 is something we're going to pass in instead. And this way we can pass in a bunch of values. And we're going to put this right here. We're going to move this into there. And then return data. So this value is in millions of light years per millions of years per millions of light years. So we actually want something besides that. We want to pass in something normal like kilometers per second per megaparsec. So in order to do that, we'll take whatever our value passed in is, and then we're going to divide that by 3.08 to the 19th. That's how it'll do the distance conversion. To go from seconds to millions of light years, we'll do seconds to minutes, to hours, to days, to years, to millions of years. So that should equal h. Now, if I say var data equals run and I pass it 70, hopefully that'll give us something similar to what we were looking at before. Whoa. No. Oh, what's this parentheses here? Do we need that? Oh, there we go. 70. And let's say we say 73. That should be the fit. Okay, so now that we have that, what we can do is we can say, once we have the data, we'll go in here. Okay. And what we'll do is we'll say for var h equals, let's go 70. And we'll say, well, h is less than 70. What we're going to do is test out different values of h. And we're going to find a best fit. So for h is less than 75. And we'll go up by 0.1. Okay. And then what we need to do is calculate SSE for that value. So what's SSE? That's the sum of squared errors. We're going to figure that out. We talked about that in the first video. So if we calculate SSE, we're going to have it pass in an h. What we're going to do is run for that h, right? I'm going to store that. Now, what we're going to do is for each supernova, we're going to look at each supernova, right, in our data set. And then we're going to calculate the difference between what the model predicts and what's actually observed. So to do that, we're going to have to go sn dot mu, and then we need to do, so we're going to do this to the power of 2. Now what is this mu here? We got to calculate that from our model. So we're going to say mu equals find z. We're going to pass it a data and then sn.z. Okay, that's not mu yet, but let's work on this. Function find z, given a data, given a z. So for var I equals 0, well, I is less than data.length, I dot dot. If the data dot z is greater than the z we're looking for, then we're going to return the last element. I think this will work. Something like that. Find z. So this is actually giving us a distance in million light years. So we need to convert that first to megaparsecs. Okay. And then we also need to multiply that by the z, because that's how we get the luminosity distance. So times z, okay, that'll give us the luminosity distance. Then to find our actual mu, we need to do 5 times math.log of 10. We can put our luminosity distance in there, and plus 25. Is that right? I think it is. Okay. So hopefully that's right. I guess we'll find out pretty soon. So now that we have a mu, we can find out the difference between them. Then we add them up. So we want to add up all the errors. So we say error equals error plus that. All right. Now we can return our error, and we're back here. So we want to keep track of the lowest error, var lowest. So we say var SSE equals that. Okay. If we don't have a lowest, or if the lowest dot SSE is greater than our SSE, gotta name that right here, then we'll set lowest equals, let's see, H and SSE. Okay. We'll do that for var lowest. Okay. And then at the end of that, console.log lowest. So let's go ahead and run this. See how bad this is. Maybe there's a bunch of errors. No errors yet. But it's not calculating. Oh, maybe it is. Okay. It's got not a number. I found the problem. Okay, so this returns that object, so I need to get its original distance. There we go. So now, if we run this, hopefully, we should start seeing. Okay, that might take a while to compute. And we're going to put something in here. Console.log HSSE. So we run this. This might be stuck in the loop. All right. Run it again. Okay, now it's actually starting to do some computing. So what it's doing is it's, for each of these values of H, it's going through and calculating that SSE. And what we're doing is we're looking for the smallest amount of errors, so the lowest SSE. And we'll see that we're going from, let's see, about 63 to 62 to 61, and then back to 62. So this 72.3, which is what we'll find out pretty soon, is what this code computes to be the proper fit for Hubble's constant. So that's really what we were going to do today, is we calculated this. This is the distances for the expanding model of the universe, and we added along the supernova data, and then we've calculated the best fit to it, and that's right there, 72.4 as Hubble's constant. All right, I hope you learned a lot. Thanks for watching.